In this lesson, we're going to be introducing reciprocal trigonometric ratios and discuss a little bit Pythagorean identities. Now, regarding the Pythagorean identities, you should be familiar with the first one from previous videos. However, the other two Pythagorean identities actually derive from the first one, but do use the reciprocal trigonometric ratios. Anyway, we're going to get there in a minute. Now, regarding the trigonometric ratios, they're in fact, the reciprocal trigonometric ratios, they're in fact the reciprocal functions of the main trigonometric functions that we know, which are sine, cosine, and tan. So the reciprocal of sine theta, which is 1 over sine theta, is in fact the cosecant function. So it's cosecant. So cosecant theta, which is denoted by CSC, that abbreviates cosecant. Regarding the reciprocal of cosine, now 1 over cosine theta is the secant function. And we have the cotan function, which is the cotangent function, which is the reciprocal of the tan function. So cotan is 1 over tan, secant is 1 over cosine, and cosecant is 1 over sine. Now, regarding tan and cotan, now it's fine, there's no confusion there. Cotan is the reciprocal of tan. But how could you possibly not confuse cosecant and secant and be able to figure out which exactly is the reciprocal of which function, sine or cosine? Well, the smallest hint I could give you is in fact that C is always the reciprocal of the S. So the cosecant, it starts with a C, now that's the reciprocal of sine. However, the secant, starting with an S, that's the reciprocal of a C, which is 1 over cosine. So always keep in mind that regarding cosecant, secant, sine, and cosine, that the C is always the reciprocal of the S. This way, you would not really confuse the functions. Okay, now moving to the Pythagorean identities. Now we've already in a previous video, when we introduced the unit circle, we've proved on the unit circle why cosine squared plus sine squared of any angle is equal to 1. Of course, as long as cosine squared and sine squared have the same angle. So the sum of these squares is always equals to 1, and we have proved that identity when we introduced the unit circle. However, over here we have 1 plus tan squared theta equals to secant squared theta. As I've already mentioned, this identity is derived from the first one. So over here, having cosine squared theta plus sine squared theta equals to 1. Since I want to reach secant squared, and we know that secant squared is in fact 1 over cosine squared, having a 1 here on the right hand side gives me the idea of dividing both sides by cosine squared in order to end up with 1 over cosine squared, which is secant squared. So over here, dividing both sides or all terms by cosine squared, that would in fact leave me with the identity, the second identity that you actually see here. Cosine squared over cosine squared is 1. Sine squared over cosine squared, that's tan squared. That's in fact sine over cosine all squared. And 1 over cosine squared is in fact secant squared theta. And it's the same for the third identity here. So again, starting from cosine squared plus sine squared equals to 1. Now over here, since I want to reach cosecant squared on the right hand side, and I already have 1 here, so I'd have the idea of dividing both sides by sine squared this time. So dividing both sides by sine squared, or all terms in this identity by sine squared. Now cosine squared divided by sine squared. Now we know that tan is sine over cosine, and cotan being the reciprocal of tan, it means that cotan theta is in fact cosine theta over sine theta. So over here we do have cotan squared theta here, sine squared over sine squared, that's a 1, and 1 over sine squared, that's in fact cosecant squared theta, which leaves me with this third Pythagorean identity. Now cosine squared plus sine squared equals to 1 is the main one. These two derive from it, and using the reciprocal trigonometric ratios. Now let's just solve a couple of examples on reciprocal trigonometric ratios and where we might have the chance to use the Pythagorean identities as well. So over here we have cosecant theta to be 5 over 3, where theta is between pi over 2 and pi. Theta between pi over 2 and pi on the unit circle, that's in fact the second quadrant. So in the second quadrant, we need to watch out for the signs of the trigonometric ratios. In the second quadrant, sine is positive, cosine is negative, which leads to a negative tan and cotan. So over here, I need to find the exact values of cosine theta, sine theta, and tan theta. Now, since cosecant is the reciprocal of sine, I can immediately deduce sine. So over here, sine theta is in fact 3 over 5. Since it's the reciprocal and cosecant is 5 over 3, then sine is 3 over 5. Now I still need to determine cosine and tan. Now over here, cosine theta is, we can deduce cosine from the Pythagorean identity, the main one, cosine squared plus sine squared equals to 1, which leaves me with cosine squared is 1 minus 9 out of 25, which leads me to a 16 out of 25. So cosine theta would in fact be 4 over 5, or cosine theta is negative 4 over 5. However, I need to check which one is rejected based on the domain given for theta. We're in quadrant 2 between pi over 2 and pi, so cosine is negative in that case. So it's the positive value of cosine that is rejected. So I have here cosine theta equals to negative 4 over 5 and sine theta equals to 3 over 5, which leaves me with tan. Now, to determine tan, the easiest way to do that is, in fact, work on tan as the ratio of sine and cosine. So tan theta is sine theta over cosine theta. So dividing 3 out of 5 by negative 4 out of 5, that leaves me with negative 3 over 4. Now, knowing the second Pythagorean identity, since I have cosine, I can have secant, and I could find tan using this Pythagorean identity, but over here this is a longer process. Since I already have sine and I already have cosine, I can immediately find tan using sine over cosine. Now, tan in that case is useful in case for example, I have cosine and I do not have sine, for example. So instead of looking for sine the way we did, we could just immediately use this identity in order to find tan. Okay, so now in this last example, I have tan, and I want to find the exact values, the possible exact values of cosine and sine. Now, this is a case where I have tan and I need to find cosine, and I do not have sine. I need to find it as well. So over here, I cannot use the main Pythagorean identity. So having tan and I want to find cosine, so I could use the second Pythagorean identity that relates secant to tan. By finding secant, we could in fact find cosine. So over here, we know that secant squared theta is 1 plus tan squared theta. So secant squared is in fact 1 plus 16 out of 9, which is a 25 out of 9, which leaves me with secant theta equals to 5 out of 3, or secant theta is negative 5 out of 3. Now notice that here in the given, we do not have a domain for theta. We know nothing about theta, where it's located exactly on the unit circle, in which quadrant. And this is why in the question they ask for the possible exact values. So here there are no values that get rejected. So I need to keep both. So so over here, since secant theta has these two possible values, I can deduce the possible values of cosine. So cosine is 3 out of 5 in this case, and in this case cosine is negative 3 out of 5. Now I need to deduce sine. Okay, so since I do already have two possible values of cosine, using the main Pythagorean identity, I could deduce two possible values of sine as well. So, but however, using the the main Pythagorean identity, cosine would be squared, so you'd notice the negative is irrelevant here. So let's just start by finding sine squared. So I have 1 minus cosine squared. So in both cases, the square of cosine is 9 out of 25, which leaves me with 16 out of 25. So sine theta is 4 out of 5, or sine theta is negative 4 out of 5. Again, I cannot reject any of these values since I do not have a domain for theta. However, here I need to relate each value of sine to one of the two values of cosine, because they do come in pairs. So over here, if you'd notice that tan is positive, and tan being sine over cosine, tan being the ratio of sine and cosine, so for this quotient to actually be positive, then sine and cosine have the same sign. So over here, if sine is positive, cosine has to be positive, and if sine is negative, cosine has to be negative. So this is how we'd actually allocate each of the values of sine to one of the values of cosine. So over here we do have these two sets of solutions to this question. So cosine theta is 3 out of 5, and sine theta is 4 out of 5, or the other possible solution is cosine theta equals to negative 3 over 5, and sine theta is negative 4 out of 5. So this pair of values of cosine and sine, in fact, is one solution to the problem, and this other pair is another solution to this problem. We'd have to join these pairs together in order to give the correct solutions to the problem. Of course, over here, following any indication we have in the given, like for example here, we had that tan is positive, so we knew that cosine and sine must have the same sign. They should both either be positive or both either be negative.